Okay. Good morning, class. Welcome back. We were discussing about pile foundations, right? So in the pile foundation, we have already seen these different classification system of the piles, right? So and then we have seen the load carrying capacity of the piles. Okay. So in the load carrying capacity, we have two methods. One is a static approach, and then the dynamic approach. And another thing is that in the load carrying capacity itself, it is a these field test. Okay, so the payload test we will call them. Okay, so then we will see those. See these payload test just to check whether that whatever calculated load carrying capacity is can be achieved or not in the field. Okay, so again those are called as these payload test. Okay, so today I am planning to cover them also. So first I will start with one more problem. We already solved one problem on the pile load carrying capacity of the sorry, the load carrying capacity of the pile. Okay, so all of you can hear my voice, right? Huh? Okay.
Yes, sir.
Yeah. Let's go to whiteboard. Okay. So take down the problem. This problem we'll see. Uh, yeah. So here, in my previous class, I have solved a problem in a uniform layer of soil. Okay, so what if you have a layered soil? Huh? So then layered soil, that layered side, it may be purely sand. All the layers are sand, or it may be combination of sand and clay. Okay, so let me first solve a problem like in layered soil, which is having a different these sand layers. Okay, so let's draw the figure here. So this is the pile, hmm? And this is your ground level. Okay, so then this is another layer, soil layer, and here we have another soil layer. Okay, so this is the ground level here. So this is ground level. Hmm? Uh, so this is at 0 meter level, and this is -4, and this is -9, and your pile will be terminated at a depth of -14 meter. Okay, so all these are in the meters. So then uh, then this depth is what is the depth of this soil here? It's a 4 meter, and so this is 4 meter depth, and see this is sorry, I think -14 here. Alright, here -4 meter it is. So what is the depth of this meter? This soil layer? This soil layer depth is around 5 meter. And this soil 9 minus 14 is again it's also 5 meter. Okay, so this is also 5 meter depth. Okay, so here you have a water table. You have a water table here. So it is at a depth of 2 meter. At a depth of 2 meter, we have water table. So top layer, this layer is loose sand. This is loose sand, and this is medium dense sand. Medium dense sand. And this layer is dense sand. Okay, so loose sand, medium dense sand, and dense sand. 3 layers of soils are there. So the unit weight of this loose sand is around 17 kilonewton per meter cube. And the unit weight of this sand layer is 18 kilonewton per meter cube. Okay, and the unit weight of this bottom, the dense sand layer, is around 20 kilonewton per meter cube. Okay, and the angle of internal friction for this loose sand, that is phi dash, is equal to around 30 degree, and angle of internal friction for medium dense sand is around 34 degree, and angle of internal friction for this dense sand, is around 39 degree. Okay, and K value. Okay, so K value for this loose sand. So usually K will be taken for a driven pile 1 to 2, right? So if you remember your these lateral earth coefficient, it will be for driven pile, it will be 1 to 2. Okay, so if it is a loose sand, you take 1. If you have a dense sand, then you take 2, or if you have a medium dense, then you take in between 1.5. Okay, so this K value they may give or may not give in the problem. Okay, so but you have to remember this range. K always you can take from between 1 to 2. So K value for this K is equal to 1. Okay, so for this layer, K will be around 1.5 because it is a medium dense. Since it is a dense sand, here I will take K value as 2. Okay, so these values they may give or may not give in the problem. Okay, so but you should know the range of this K value. Okay, then what else we need? We need delta also, no? So because to calculate the skin friction, I need a delta value. Okay, so delta for this loose sand, according to your IS 2911, you can take equal to 35 value. Okay, so or sometimes some researchers what they suggest is delta you can take 2 by 3 times 5 value for these driven piles, and for cast in situ pile you take a delta is equal to 5 value. Okay, so some researchers they will tell like this. Okay, but IS 2911 IS 2911 will tell you this delta you always take equal to 5 value. Okay, anyway, I will take a delta is equal to 5 value. Yeah. But even if you calculate with 2/3 of 5 value is also fine. So delta is equal to 5, that is equal to 30 degree. And here delta is equal to 5 is equal to around 34 degree. And delta is equal to 5 is equal to 39 degree. Okay. So these are the parameters we need. Okay, so whatever with the blue ink I written, no, with blue ink whatever I written, those things are the given parameters. Okay, so these black ink parameters, they may give in the problem or they may not give. Okay, it's not mandatory that they should give these parameters in your problem statement, because these you should remember. What is the range of k value and what is the range of delta value. Okay, so once we know the parameters, next thing is I need to calculate the overburden pressure. Okay, so to calculate overburden pressure, I'll draw a line here. So up to here, okay, up to your tip of pile. So pile tip is here. Okay, so now up to this, see, one more thing here, they given simply unit weight. Okay, so that means these dry unit weight and saturated unit weight, they are considering same. So if they're not given saturated unit weight exclusively, then what you can do, whatever dry unit is there, no, that only you consider it as a saturated unit weight. Okay, in this problem they're not given separately. So this whatever bulk unit weight they given, that I will consider dry on the above water table, and below water table whatever soil is there, that I will consider it as a saturated unit weight. Okay, so for the first 2 meter, what is the these overburden pressure? First 2 meter, so at 2 meter depth, this is nothing but 17 into 2. So this is 17 into 2. How much? 34 kilonewton per meter cube. Okay. Then next, for the another 2 meter, it is a saturated unit weight. Okay. So this is at 4 meter depth. 4 meter depth of the pile. So here 34 plus, I have to take the submerged unit weight here. I have to take a submerged unit weight. What is this? 17 minus 10. Okay, 10. I will consider 10 as a unit weight of water. So 17 minus 10 is 7. Okay, so 7 into what is the depth here? 2 meter. So how much you are getting? How much? Tell me. Are you able to hear my voice, right? Please respond, anybody. 48 kilonewton per meter cube. Okay. Okay, so in between, please talk. Otherwise, I will what will happen? I will think that that's network is lost. So whenever I will ask, please respond, because we have a lot of this network problem will be there here. And then see here it is a sandy soil. Now that critical depth approach you can employ. Okay, so you have two options. Either you can follow the critical depth approach, or you can take a full these lateral earth pressure. Okay, so but I will follow the critical depth approach, but you take it as a homework, and you don't consider critical depth and take the full variation of your lateral earth pressure, and then you again you calculate the load carrying capacity. Okay, so that will be your assignment question. So here I will consider, because it's a dense, it is a sandy soil. See, always this critical depth concept will come into picture wherever you have a sandy type of soil. Okay, because whatever this why this critical depth concept is coming, because of the soil arching. Okay, so soil arching will take place always in the sandy type of soil. So soil arching is nothing but if there is a relative displacement between soil and the pile or whatever material inside you insert the pile, inside the soil. If there is a relative motion between these two what you call mediums, then the soil arching phenomena will come into picture. Okay, so here pile is moving relative to sand. Okay, so that's why this this what you call soil arching will takes place. Okay, one more example for soil arching is like, say, your what do you call these underground pipes and also your culverts. Okay, so if you see these culvert pipe they will install, no, to just to facilitate the drainage of this water drainage in the roads and all. If you would have come across, like some bridge will be there. Okay, so if this is your road, below this road some concrete pipes will be put, right? So all along perpendicular to your road. So just to facilitate the drainage of water. Okay, so here also this pipe and soil will be there. Okay, so here also that the soil arching concept will come into picture. So you have two options here. Either you take because this is a still debated topic. Some people, they will tell in the field you won't experience the soil arching, but some people will tell you have to consider the soil arching. So if you solve it with any method, that is also fine. Okay, so I will take by considering soil arching. So I will calculate the critical depth. Okay, so this DC, that is critical depth, is equal to 15 to 20 times your diameter of the pile. Okay, so since I have a loose sand and medium sand, no, so in the majority part is loose to medium sand. Okay, so I will take it as a 15 times. So 15 into, what is the diameter of the pile? So diameter of the pile is 350 mm. 350 mm is the diameter of the pile. Okay, so 15 into 0.35. So what is the critical depth you are getting? BC, tell me.
5.25.
How much you are getting? 5.25. Okay, so 5.25 meter is my critical depth. Okay, so let us draw one more line here. So this is my DC. Okay, 5.25. Very good. Okay, so up to here it will vary. Once we reach the critical depth, then the variation I will take uniform. Okay. So what is the earth pressure here at this level at 5.25 meter? So 48 plus up to 4 meter I calculate. Now how much remaining? Remaining is 1.25 meter. From here to here, the length of the pile is 1.25. So 1.25 into your density. Density is 18, no? So 18 minus your unit weight of water, I will take it as a 10. Okay, so 18 minus 10 is 10. Sorry, 8. 8 into 1.25 into 8. Okay, I will write it here. 1.25 is your depth. 8 is your submerged unit weight. Okay, so how much you are getting?
58.
Sorry. How much? 58. Yeah. So 58 kilonewton per meter square. Okay. So this is cube I written. Okay. Sorry. This is meter square. Okay. Because it is a stress, no? So it is a stress meter square. Here also meter square. Meter square. Not cube. Because it's a stress. Kilonewton per meter square. Kilonewton per meter square. Okay, so same thing. It will up to tip of the pile will be same, around 58 kilonewton per meter square. Okay, so this is at a level of 14 meter. So this is at the level of 9 meter, and this is at level of 14 meter. This is your length. Along the length of pile, how the earth pressure will vary. Okay, so up to critical depth, linearly it will increase. Once it reaches the critical depth, then uniformly it will the stress will be uniform. That is your arc pressure will be uniform, not arc pressure, your overburden pressure. Okay. Now, so first, what I will calculate the end bearing. Okay. So whatever end bearing is there, that I will calculate. This is my QB, and this is my your QS. This is my QS. Okay, first I will calculate the QB value. Okay, so how I can calculate first this QB. QB is equal to, what is the formula? Or QBU I will call. Okay, so QBU is equal to Q or sigma bar NQ. Okay, sigma bar into NQ plus 0.5 gamma D, that is the diameter of the pile. 0.5 gamma D into N gamma. Okay, this is your unit Q, small q BU. Okay, so this entire term is small q BU, that is unit this bearing intensity. Okay, into cross sectional area. Okay, so anyway, this circular pile, so cross sectional area will be pi by 4 into, what is the diameter of the pile? Diameter of the pile is 350 mm. Okay, so 0.35 square. Right? Square. Okay, so what is the sigma bar at the tip of the pile? Tip of the pile around 58, right? So 58 into NQ. See, NQ, for the NQ, I have to refer IS 2911. Okay, so for N gamma, what I have to refer? IS 6403, table number 1. Okay, so let us first see NQ value from IS 2911. So let us go to 2911. It's what kind of pile it is? It's a driven pile. Okay, so I have to go for the, I think section 2 is for driven pile. Okay. So this is board cast institute. It's a board pile. Driven is section 1. Okay, so I have to refer to section 1. Sorry. One more thing I should write here. It's a driven pile. Okay, so let us write it here somewhere. Driven pile it is. Okay, so for the driven pile, I should refer section 1. This part 1. Driven cast in situ pile. So here I have to go to the end. There is a chart is there. Okay, you see this annexure B. So this annexure B, I should refer load carrying capacity. Even if you don't remember the formula, see formula also given in the code itself. This formula also given in the code. So here I have to get first is NQ value. Okay, so how I will get the NQ value? Yeah, see, bearing capacity factor NQ for driven piles. So what is the phi value here at the tip of the pile? At the tip of the pile, phi value is 39 degree, right? So for this 39 degree, I should get a NQ value. Okay, so where is my? This is 35. So 39 is somewhere here, right? So correspondingly, this is 100, 200, 300, 400, 500. Okay, so this is 150. So you can take it as 130. That is my NQ. Okay. So 130. See, either you can take 130 or see, I calculated by taking 132. Okay, so I will stick to 132 because all my answers are according to 132. Hmm? So either you can take 130 also fine, even 132 also is fine. It is not going to differ much. So from IS 2911, what is the figure number here? This figure number is 1. From figure 1. So from figure 1, what is my NQ value? 132. Okay. And for n gamma, see this thing you can neglect. Okay, so if you don't want to calculate, you can neglect this term. So I will see, this is optional. Either you calculate this term or you can neglect also. So I generally people will neglect this, but IS 2911 they will consider this term also. Okay, so I have calculated by considering this. Okay, so stick to that. Okay, so you consider this just to get n gamma. How I can get n gamma? I have to refer to 6403. Okay, so let's go to 6403. 6403 I have put in shallow foundation chapter. So this is my 6403. Okay, so here in the 6403 table number 1 I should refer. So my phi value was 39 degree, right? So 39 is almost like 40 degree. Okay, so it is a 109.41. So you need not to interpolate. Okay, if you want to interpolate, you interpolate, but I will consider it as a 109 because see, for 39 degree I don't have these phi value. Okay, so nearest value is 40 degree. For 40 degree is around 109. Okay, so if you want to get the accurate value, then you have to interpolate. Okay, you have to interpolate between 35 and 40. In between that 39 will come. Okay, so little lesser than 109 you may get. Okay, so but I will consider it as a full value. Okay, so this for 40 degree only I will take 109.41. So phi value is equal to your n gamma value. So n gamma is equal to 109. I will consider 109.41. Okay, now put it everything here and then get the QBU value. Okay. So now your QBU is equal to 58 into NQ. NQ is how much? 132 plus 0.5 gamma. Gamma is again submerged into weight I should take. What is the submerged into weight here? 20 minus 10. Okay, so that is 10. 0.5 into 10 into diameter of the pile. This is D is diameter of pile. 0.35 into n gamma. N gamma is 109.41. Okay. Multiply by your how much you got here? The cross sectional area. How much you got? 5 by 4 into 0.35 is square. Around 0.096. 0.096 meter square. So that I will write here 0.096 meter square. So tell me how much you are getting? QBU. That is the base resistance. The base resistance I am getting around 755 kilonewton. So this is my first answer. Base resistance I got that. Okay, next I have to calculate the shaft resistance. Okay. Shaft resistance. Okay, so for the shaft resistance, I will start from the bottom. Okay, so first I will calculate the shaft resistance between 9 meter and 14 meter, and then between 5.25 and 9 meter, and then between 4 meter and 5.25 meter, and then from between 2 meter and 4 meter, and from 0 to 2 meter. Okay, so this I will call as QSU1. Okay, this is the first shaft, second shaft, third shaft, fourth shaft, fifth shaft. Okay, so like that, a 5 shaft resistance I should calculate. So let us first QSU1. Okay, so first shaft resistance, that is your sigma average. What is the formula? Sigma average into k times. Okay, so that is sigma average into k into tan delta into what? Into surface area. What is the surface area? Surface area is the pi into d into L. Okay, the pi into d is 0.35, and what is the length here? So this I am calculating between what? Between 9 and 14 meter. So between 9 and 14 meter I am calculating. Okay, so that means what is the 5 meter? No, yeah, that the length of the pile is 5 meter. Okay, pi. This is pi d L. L is how much? 5 meter. So what is the sigma average here? You see, refer to this overburden pressure distribution diagram. So at the middle, that is 58. Okay, so here uniformly it is distributed 58 kilometer. So 58 into k value. What is the k value I have taken here? K is 2 here. Delta somewhere, delta is 39. Okay, because delta is equal to 5 degree, I have to consider 39 degree. So tan 39 into pi into 0.35 into 5. How much you are getting? QSU1. How much?
516.
516 kilo Newton. Okay. Next I will calculate the shaft resistance between 5.25 and 9 meter. Okay. That I will consider. I will call it as QSU2. Yes, that is from 5 to 5.25 to 9 meter. So that is between 5.25 meter to 9 meter. Okay. So calculate same thing, because sigma average is same only, because here also it is uniformly distributed. No, so it is uniformly distributed. So take 58. So 58 into k is what is the k value for the second layer? K value here it is 1.5. I have to consider 1.5. 1.5 into tan of what is the delta value here in this layer? In this layer, delta is 34 degree. Okay, tan 34 into pi into d. D is anyway 0.35. 0.35 into what is the L? 5.25 minus 9. How much? 3.75. Okay, calculate how much you are getting. Tell me.
241.9.
241.9.
Okay, 241.9. I will consider it as 241 kilometer. Next, QSU3. Huh? So QSU3 is what? That is the shaft resistance. This is QSU1, this is QSU2, and this is QSU3. That is between 4 meter and 5.25. Between 4 meter and 5.25 meter. Okay. So here, so I have to take the average. Average I have to take. So that means half 1 by 2, 48 plus 58. That is my sigma average. So half 48 plus 58. Okay, that is my sigma average into what is K value? K value in the third layer. Okay, so this is first, this is second. So this is 5.25. That is QSU3, no? Okay, so K value is still 1.5 meter only. Okay, so K is 1.5. So 1.5 into tan of 34. So tan of 34 into pi into D into L. What is the L? Between 4 meter and 5.25, that is 1.25 meter. Okay. Calculate how much you are getting.
73.7.
Very good. 73.7. Okay, so I can let me cancel 7 kilo. Okay, then QSU4. QSU4 is from where? You see, QSU3, QSU4 between 2 meter and 4 meter. Between 2 meter and 4 meter is equal to half into, let us see what is the average overburden pressure. Sorry, overburden pressure. 34 plus 48 divided by 2. 34 plus 48 divided by 2 into what is the K value? K value, I think it's 1 into tan of how much degree? Tan of 30 degree. Tan of 30 degree into pi into D into L. L is what? 2 meter. Yeah. How much?
52.05.
Yeah, 52 I will consider. 52 kilo Newton. Okay. I think one more layer is left now. So QSU, yeah, this QSU 5 I will take. Okay, so this is QSU 5 between 0 meter and 2 meter. So QSU 5, that is from 0 to 2 meter. Okay, so again half 0 plus 34, no? Into 1 into tan 30 into pi into D into L is 2 meter. So tell me how much you're getting.
21.5.
Yeah, 21 and 21 kilo meter. 21.58 you are getting. So
21.5.
Okay, I will consider it as 21 kilometer. Now you add up all. So my total Q shaft resistance, shaft ultimate is equal to what? QSU1, QSU2, QSU3, QSU4, QSU5. Okay. So if you add all the parameters, how much you are getting? You tell me. How much? QSU. If you add all these parameters, you will get 903.7 kilo Newton. So now, what is Q ultimate? Q ultimate is equal to Q base ultimate plus Q shaft ultimate. Okay, so this is my second. Sorry, okay, base ultimate, how much I got? 755. 755 plus 903. I'll take this as 903. How much you're getting?
165.
1658 kilo Newton. Okay, so this is your ultimate load carrying capacity of the pile. Okay, so this much load it can take. Okay, but what is the allowable or Q safe? This is ultimate. Okay, so this much, if you put if this much load, then pile will fail it. Okay, so that's why safe load is Q safe is equal to Q ultimate divided by factor of safety. So 1658 divided by, you take 2.5 as a factor of safety. Okay, some people may take 3 also. Okay, that is also fine. I will take 2.5. Okay, how much you are getting? Six 663 kilo Newton. Okay, so this much load safely you can apply. Okay. Any doubt here in this problem? Any doubts are there? No? Okay. Then we'll go to the one more problem. Now I will take a pile, but in different layers. So like in that layer, sand also is there, and even clay is also there. Okay. So I think it's 45. That will take little more time. Okay, so that problem I will solve in the tomorrow's class. Okay, since we have another 15 minutes, I will take another a theory portion. Okay, so because that problem I may require half an hour to solve that problem. Okay, so again it will become incomplete. So tomorrow I will take that problem, but today I will cover one more concept. Okay, so that is your pile load test. So load test on the pile, or pile load test we will call. See, till now whatever this static approach we have calculated, no, we have seen this static approach to calculate the load carrying capacity, right? So see, we have to see in the pile there is a lot of problem about this quality control. Okay, in the field, even though you would have designed perfectly in the lab, in your design lab. Okay, but while execution there will be always a lot of constraints will be there. Okay, so you will be having some defects. Okay, so if you see here some examples of pile defects, you see there is no concrete at all at certain depth. When we will pour the concrete from the top, no, so here all concrete is not at all here. And you see this figure, and you see these figures. Okay, a lot of quality control issues will be there. So to ensure all the piles are in good condition and should take whatever your design loads are there. To ensure that we have to test these piles before constructing your superstructure. So before constructing superstructure, I have to test these piles. Okay, so just now we have calculated. Now how much we calculated Q safe? Q safe we calculated around how much? Just now in the problem, around 663 kilonewton we calculated. No, 663 kilonewton we calculated. For example, I am telling. Okay, so this is for just for example's sake. whether this much load, whether it can really take or not, I have to check before constructing your superstructure, because always there will be some quality control issues will be there in the pile casting. Okay, that's why I told always these pile foundations are a specialized work. Okay, so not every contractor can do this work. Okay, so there is a specialized contractors will be there. You have to employ them only. Okay, so then only you can ensure good quality of these piles, because once you casted a pile inside the ground, you don't know what is happening inside the ground. Okay, because it's you can't see that. So that's why these quality control issues will be there. So to ensure that whatever your safe load or design loads are there, that much load, whether these piles really can carry in the field or not, you have to test them. Okay, so that's why these are called this topic is very important. Okay, so load test on the pile. So the pile load test is the direct method of determining the allowable load. Okay, so you see, this is the direct method of determining the allowable load. So we have the indirect method. What are those indirect methods? That is static approach is there, no? The static approach or your dynamic approach, both are indirect method. Okay, so this is the direct method to determine the allowable load on the pile. Okay, so it is considered to be a most reliable of all the methods. So whatever your static approach and even dynamic approach. Okay, anyway, dynamic approach I have not covered, but in the later stage I will cover it. Okay, so that is also a way of obtaining the load carrying capacity. Okay, so how we obtain the load carrying capacity by static approach. No, similarly there is another approach, that is dynamic approach. Okay, I will come to that in the later stage. So among all the three methods, this is more reliable, because actually you are testing in the field. So there are three types of tests. Okay, so one is the vertical load test. So vertical load test means that is compression test. That is to establish a relation between load and settlement of the pile. And another type of pile load test is lateral load test. Okay, so lateral load test, it is meant to check the lateral load carrying capacity of the pile. And the third type is the pull-out test. Pull-out test to check against uplift load. Okay, because see, whatever this pile you have installed, no, these piles will be subjected to these three types of combined loading. Okay, so suppose this is your ground, and this is your pile. This is your pile, and this is your pile cap. So some pile cap will be there. That pile cap will be above the ground. Okay, so these piles, it will be subjected to three types of loading. What are those three types of loading? First is anyway the vertical load, that is compression load. And then it will be also subjected to lateral load. It will be also subjected to, this is lateral load. This is QV, and this is Q lateral, QL. And then what is the another type of loading? It can also be subjected to is a pull-out. That is uplift pressure will be there, because what will happen in the water, whenever you install these piles in the water or swelling type of soil, or even if you install these piles to resist the pull-out loads. To resist these pull-out loads, so like your anchor load, whatever these anchors, they will in offshore structures they will build these anchors. So these anchors will be, see here, if you would have visited your this port structure, what will happen once this boat will come? No, suppose this is your sea port. Once the boat will come, you have to anchor these. No, you have to anchor these boats. So to anchor them, there is a very huge anchor facility will be there. Okay, so that facility will be supported with the piles. Okay, so those piles will be subjected to your pull-out load. So if you expect that some of your piles are experiencing this kind of pull-out load, then you have to test these. You have to test for these pull-out test also. or if you are sure that your pile is only subjected to vertical and lateral load, then you can do only these two tests. Okay, so you can skip this test. Okay, suppose if you have a multi-story structures, or if you have these transmission lines. Okay, usually in the transmission lines also you may expect these pull out loads will be there. Okay, so in those kinds of piles, you have to test for these pull out load carrying capacity also. Okay, so these are the three different types of tests which can be performed on the pile in field. Okay, so again, there are mainly two categories of pile load test. Okay, so what do you mean by the two category? We will see here. First category, we will call it as an initial test. So first category of the loading, we will call it as initial test. Okay, so these initial tests are nothing but it is a destructive test. It is a destructive test carried out on piles which is not a structural pile. What do you mean by that? That structural pile. So that whatever pile you will choose, whatever pile you will choose for the initial test, those piles will not participate in load carrying mechanism once you build your superstructure. Okay, so whenever, see, in my beginning class itself, I told whenever you are casting the piles, we will cast some extra piles. We will cast some extra piles. Okay, so those extra piles will be used to do these initial tests. Okay, because once you do the initial test on these piles, you will entirely you will apply the load on this pile until it will fail. Okay, so until the pile will fail, until that you will apply the loads. Okay, those tests are called as initial tests. So that's why it's called as a destructive test. Okay, so that's why it is a destructive test. Why I am calling it as a destructive test? Because I am applying the load on the pile until the pile will fail. Okay, so that's why it's called as a destructive test. So that it is not used for carrying the load from the structure. Okay, that's also I covered. The piles are loaded to failure or at least twice the design load. Okay, so either you apply the load on these selected piles until it will fail, or you apply the load twice so your design load. Okay, whatever design load is there, that double that load you apply. So initial tests are also serves the purpose to set the limits for limits of acceptance for a routine test. Okay, so I will discuss about this routine test. Okay, so what I told, there are two categories of pile load test. One is the initial test, and the other one is the routine test. Okay, so to do the routine test, it will set limitations like how many piles you should test in the routine test. Okay, so that idea you will get once you do these initial tests. Okay, so usually what will happen? Usually 1 or 2 tests are adequate for the initial load test, because it's a very costly affair, because you are failing entire pile. Because see, the casting itself is a very costly affair. Then after casting, you are failing. You will apply the load until it will fail. Okay, that means this pile will not be useful after this initial test. Okay, so it's it will not participate in load carrying mechanism. So that's why it's a very costly affair. So that's why we will test only maximum 1 or 2. If it is a very big project, then 2 tests, or if it is a very small project, like some one residential complex, then one usually they will do 1 test, and the max 2. Then there is another type of test that is called as routine test. In the routine, see, in the initial test, what we did, we applied the load until the pile will fail. But here we will not apply the load until the pile fails. We will apply only half the working load. Okay, that means 50% we will apply. Okay, suppose my 900 kilonewton is my working load. I will apply only around 450. Okay, half of that load I will apply. That means I am not going to allow the pile to fail entirely. Okay, so those types of tests are called a routine test. Okay, so these piles, whatever piles you will test in the routine test, those piles will participate in load carrying mechanism from your superstructure. Okay, So you are not allowed to fail that pile entirely. Okay, so that means you will apply only 50% of the load you will apply, and you will check how much settlement is occurring. Okay, so if those settlement under that 50% load is acceptable, then you can tell that, okay, so the whatever work has been done, the quality is of a good quality control is achieved. That conclusion you can draw from these routine tests. Okay. Now you understood now the difference between the initial test and routine test. So I will repeat once again. Initial tests are meant for the destructive test. Destructive test means the load will be applied on that pile until the pile will fail, or double the design load. Until that you can apply the load on the initial test. Okay, so whatever the piles you have chosen for the initial test, no, those are extra piles. While before casting, before your superstructure can transfer the load, so you already in advance you would have decided that where you want to do these initial tests. Okay, so those extra piles you should cast in the field. Okay, so only those piles only you have to go for these initial tests. Okay, so once you do the initial test, it will tell you broadly, it will tell you what is the quality control you have achieved. Okay, so based on that, then you can decide how many piles should be tested under a routine test category. Okay, so based on that you can decide. Okay, so in the routine test you will apply only 50% of the load. Okay, any doubt here? Okay, I think it's almost 10 o'clock. Okay, so I think your next class will be scheduled. So I will stop it here. So in the next class, I will discuss these, how we can do these pile load tests in the field, how we can do these pile load tests, and then I will solve one more problem on the layered soil by static approach. Okay. So any doubt, any clarification you require regarding today's class? You need any clarification regarding that today's class, whatever we have learned today? Aishwarya, any doubts?
No, sir.
Okay. Prajwal, are you there, Prajwal? Prajwal Shetty?
No, sir.
No doubts? Okay, so in that case, I will stop the recording here. Stop recording.